When astronomers first tracked 3I, Atlas, the third confirmed interstellar visitor to enter our solar system, they expected another comet or asteroid. Something familiar, something explainable. Its trajectory clearly identified it as a body from beyond the solar system, and the initial brightness measurements revealed a faint tail stretching behind it. That, on its own, was not unusual. Comets shed gas and dust when they near the warmth of the sun, and tails are their most recognizable feature. But the behavior of Atlas's tail stirred far more attention than its mere existence. NASA researchers analyzing high-resolution imagery and photometric data found that its shape, flow, and persistence didn't match the standard textbook definition of cometary dust behavior. Instead of dispersing chaotically like a mist, its tail appeared structured and directional, resembling controlled emission rather than random sublimation. The most striking feature was the stability of the plume. Typically, cometary tails bend and warp under the constant buffet of the solar wind and radiation pressure, shifting direction like smoke in the wind. Yet Atlas's tail maintained a coherent line, as though unaffected by the turbulence around it. Even more curious, astronomers noted variations in brightness along its length, almost as if the emissions were occurring in pulses or bursts. To some specialists, the resemblance to propulsion was impossible to ignore. Unlike diffuse cometary dust, this tail seemed deliberate, projecting like a thrust plume instead of fading into space. NASA did not casually admit that Atlas's tail looked more like propulsion than dust. The phrasing came after weeks of computational modeling and spectroscopic analysis. Natural explanations were tested. Sublimating ices, boiling organic compounds, scattering dust grains. Yet the observed signatures were faint, inconsistent with what the geometry of the tail suggested. More importantly, the energy budget didn't add up. The level of sublimation required to sustain such a consistent plume was far beyond what the object's surface area and solar heating could support. This mismatch pushed scientists toward uneasy territory, where natural explanations strained credibility, and propulsion-like comparisons became unavoidable. The memory of earlier interstellar visitors framed the debate. When Oumuamua crossed our solar system, its unexplained acceleration sparked arguments over whether subtle jets of outgassing could explain its motion. The absence of a visible tail left the question unresolved. Later, 2I, Borisov reassured astronomers by presenting a classic cometary profile, with a spectacular dust tail consistent with expectations. By the time Atlas arrived, scientists anticipated something similar. Instead, its strange, structured plume forced them to reverse their assumptions and confront the possibility that they were seeing something far less ordinary. This doesn't mean Atlas is artificial in origin. There are natural processes that could mimic propulsion, such as focused vents beneath crusts of frozen gases releasing material in tight plumes, or cryovolcanic activity ejecting matter in bursts. But for these to occur, the body would need very specific conditions, statistically unlikely for a random interstellar fragment. NASA's careful wording acknowledged this tension between improbability and impossibility. They weren't declaring alien technology, but they were admitting the phenomenon defied easy categorization. One of the most intriguing implications is how Atlas challenges the very definition of cometary behavior. In recent decades, the line between asteroids and comets has blurred with discoveries of active asteroids and dormant comets that flare back to life. Atlas adds a new twist. Interstellar bodies may carry chemistries unlike anything in our solar system. Exotic ices could release gases at different thresholds, producing effects unfamiliar to us. What looks like propulsion may simply be the natural expression of alien chemistry, teaching us that star systems beyond our own do not necessarily follow the same rules. Still, the propulsion analogy lingers, and with it, the question of artificiality. The SETI community has long argued that alien artifacts might reveal themselves not through flashing beacons but through anomalies, strange trajectories, unexplained accelerations, or emissions inconsistent with natural processes. If an interstellar probe were coasting between stars, it might rely on efficient propulsion systems that would look to us like Atlas's structured tail. Clean, linear plumes of expelled matter could be the exact kind of signature one would expect to see from such a craft. Even without claims of alien engineering, the event carries weight because of NASA's transparency. Acknowledging the resemblance to propulsion reflects a cultural shift in space science, a willingness to describe what is observed without forcing it into conventional categories. For younger astronomers, this signals a new era of honesty. Anomalies must be reported as they are, even if the language invites speculation. Saying the tail looks like propulsion is not the same as claiming it is propulsion. It is simply recognizing that by human standards of physics and mechanics, the closest analogy we have is a rocket exhaust. In the end, 3I, Atlas leaves us with more questions than answers. Its tail remains a puzzle, too structured for comfort, too stable for easy classification, too evocative of engineered systems to ignore. Perhaps it is simply the product of exotic chemistry, a reminder that the universe's diversity will always surprise us. Or perhaps it hints at something greater, a visitor whose story we can only begin to glimpse. What is certain is that humanity has witnessed yet another moment when the cosmos refused to fit neatly into our assumptions, and for that reason alone, Atlas will be remembered as one of the strangest travelers ever to pass through our skies. When astronomers initially discovered 3I, Atlas, the third confirmed interstellar object to enter our solar system, they anticipated typical comet behavior. At first glance, it seemed to conform to that expectation, showing a faint tail as it approached the sun's warmth. Comet tails usually occur when solar heat prompts ices to sublimate, releasing gas and dust into space. However, researchers soon observed unexpected traits that deviated from their predictions. The tail of 3I, Atlas didn't appear as a diffuse mist of chaotic particles. Instead, it exhibited a structured, stable, and directional plume, resembling thrust rather than a natural cometary tail. This unique stability, along with brightness variations hinting at pulsed emissions, led NASA to recognize it as having a propulsion-like quality. Typically, comet tails change shape under solar wind influence, bending and twisting continuously. In contrast, this tail maintained a coherent line, suggesting that its emissions might be intentionally guided. NASA scientists conducted models and simulations to rationalize this through natural phenomena, yet the data failed to align. The energy output observed was inconsistent with the heating the object should have received from the sun. Additionally, the absence of typical organic signatures further deepened the enigma. The emerging comparison with propulsion became inevitable, though researchers hesitated to label it as artificial. This wasn't the first instance of astronomers confronting a similar enigma. When Oumuamua traversed the solar system in 2017, its inexplicable acceleration raised questions, despite lacking a visible tail. Later, the arrival of 2I, Borisov, which behaved like a classic comet, reassured scientists that not all interstellar objects were anomalies. However, 3I, Atlas once again defied expectations, compelling astronomers to accept that some interstellar visitors do not fit neatly into established categories. Some scientists proposed natural explanations for the phenomena. Cryovolcanism, for example, could generate focused jets if vents formed beneath frozen layers of exotic substances. Rotational dynamics might also align emissions to mimic propulsion. Others speculated that unfamiliar ices from outside our solar system could sublimate in pulsed patterns, leading to sudden brightness changes. While these scenarios are plausible, they hinge on highly specific and unlikely conditions, leaving the mystery unsolved. The tail's geometry only added to the puzzlement. Unlike the diffuse spread characteristic of most comet tails, it exhibited a narrow, sharp structure reminiscent of engineered exhaust. Some experts even likened it to ion thruster emissions, which produce long, consistent streams of charged particles. Although this similarity doesn't confirm anything artificial, it emphasizes how natural and technological phenomena may visually converge. This presents an interpretive challenge. How can we differentiate between a rare natural occurrence and an authentic artifact? The implications of 3I Atlas extend well beyond itself. Future surveys might consider anomalies as valuable cases warranting deeper exploration, rather than mere errors or curiosities. Automated detection systems could be trained to identify structured emissions, pulsed activity, or coherent plumes that stand apart from typical comet behavior. In this way, anomalies could integrate into the research framework rather than distract from it. Some even advocate for a new classification of interstellar objects, designated as ambiguous, that acknowledges their uniqueness without forcing premature conclusions. The propulsion-like characteristics of 3I Atlas tie into broader questions surrounding galactic archaeology, the pursuit of evidence of extraterrestrial technology dispersed throughout space. While much of this field remains speculative, 3I Atlas serves as a tangible anomaly that could aid future searches. Even if it originates naturally, its unusual attributes may illustrate what an artificial probe could resemble if it ever passed by. For exoplanet science, this occurrence underscores the importance of interstellar visitors as carriers of alien chemistry. If these bodies contain ices and compounds unfamiliar to us, each one could reveal insights into the diversity of planetary systems across the galaxy. Studying them might uncover environments far more complex and bizarre than our own solar system. In this light, even a natural explanation would be remarkable, showcasing a new dimension of cometary physics. NASA's willingness to describe the tail as propulsion-like indicates a cultural shift in astronomy. For many years, scientists avoided such terms, concerned it might seem sensational. However, the interstellar epoch has encouraged a new honesty. If the data appear unusual, they must be reported transparently, despite any discomfort. This openness fosters curiosity, from classrooms to the public sphere. Students can learn not just about comets' mechanics but also the importance of grappling with unexplained data, keeping scientific inquiry vibrant and dynamic. Symbolically, 3I Atlas resonates with humanity's aspirations for interstellar travel. Its plume evokes an image of how our spacecraft may appear as they journey into distant systems. Perhaps we are merely witnessing a natural occurrence, or maybe we are glimpsing something more intentional. Regardless, this resemblance reminds us that the universe is alive with motion, and sometimes that motion echoes our own aspiration.